In this demonstration, we are going to simulate the one-dimensional pulse laser machining of structural alumina. We are not going to demonstrate the multipulse laser machining, but we're going to just simulate one pulse that lands on the surface of the ceramic. In the later stage, or in other videos that we're going to demonstrate, we are going to eventually show how to simulate the multiple pulses on the structural alumina as a result of laser machining. And we'll eventually demonstrate surface topography as well. So this is an article by Vora, who worked with the following authors, and it's a very interesting article which shows how laser machining can be used to machine structural ceramics, and COMSOL Multiphysics is used here. In essence, he demonstrates exactly this multiple physics that happen on the material surface as a result of the irradiation by a laser, whereby the surface would melt into a certain liquid which forms a pile up, and as it solidifies it will form a certain topography, and this pile up is caused by a plume which pushes the liquid molten material, exerting recoil pressure, and this basically is the resulting surface profile. So in a way, he demonstrates these multiple physics. Here is a typical, I'm going to zoom in properly. Here's a typical illustration where it shows multiple pulses as they land on the surface, and these are the on and off equations, or let's say graphical representations of the pulse and the temperature profiles that result as a function of these laser operations. And he demonstrates the number of pulses per second, and even I would say the residual surface topography as well. If you scroll down, you also see the workflow whereby he designed the geometry, applies the material properties, which we actually created in our previous demonstration, meshes the geometry, solves, and evaluates for temperature. We are going to focus only on heat transfer, which means it's only this section of the model. And then later in our other demonstrations, we are going to do fluid flow as well. I will also include the link at the description below of the article. This is a geometry that we are going to use as well. The dimensions here. And this is a typical workflow that he showed, and we are going to, in a way, and here we're going to just do the most basic heat transfer model. We will not remove the surface or the elements. We will not do fluid flow yet, but in this demonstration we're just going to sand just here. These are typical material properties which we were able to create, or at least include into the material that we created in our previous demonstration. And then these are the material a table showing the laser parameters, and we inserted these equations, and we're going to include all these equations here except for these, and we're not going to include the fluid flow yet, equations, not yet. So let us begin. So opening COMSOL Multiphysics here, we want to create a model, so we are going to click Model Wizard, and then we're going to select 2D. We could select 2D axis symmetric, but we will not since we are following this article. We are going to select heat transfer just in solids. We could add conjugate heat transfer, but not, because this is it's coupled with fluid flow. So we're just going to add just heat transfer in solids. The nice thing about COMSOL Multiphysics is that every time you click a physics, it gives you an explanation of what this physics is about and where it is applicable. Clicking Add, and then we're going to move to Study. It's a time-dependent study, and the description here of what a time-dependent study is. Clicking Done. So you will notice that automatically there's, let's say, 3 or 5 windows. You have the model builder window, which is similar to this toolbar up here. Then you have the setting window, which changes every time you click a certain feature of the model builder. And then you have the graphics window, which displays every plot, every geometry that you create in the model builder. And then down here, if you expand here, this is where you see the progress of the simulation, the logs, and they also display the errors. If I close this node, you will notice that the model builder has 4 nodes. The global definitions, which includes every parameter that will be used in the model or in the component. You could have 5 components here. If you include the parameters up here, they will still be applicable in every component here. And then you have the component node, where you create the model, you add the physics, you add the material properties, and you mesh everything. And then on the study node, here you specify the time dependence and the step inputs for the calculation and when the calculation is going to stop. So it starts at 0, it increases by 0.1, ends at 1. That's what typically what this means. So, but we may change it based on the computation. And then the last node is a results node, where you view all the plots, all the outcomes of the computation. So first, let us open the global definitions. If you right click here, I'm going to add the parameters. these parameters that are included in this model. So we're going to be very fast. I'm going to copy. We're using shortcuts Control C and paste. This right here. TM. So in COMSOL Multiphysics, when you add parameters or an expression, the units are always in square brackets. Here you might want to put just a symbol, not the full name. And then everything that you input here in the expression column is converted into SI units here in the value section. So you cannot edit here, but you can edit this. And then here you describe. It is always important to describe so that anyone who uses your model can follow. I'm skipping this dynamic viscosity since it's a piecewise function which we included in the material properties. We're going to select one, just 10 pulses, just 10 here. This is a this is per second, so it heads. One could write heads here, see what happens. Changes nothing really. And then we have pulse energy, which is 1 joule. And then we have ED, which is the corresponding average laser energy density. I'm going to just paste it here. It has a formula, which is EP over EP times F over pi over 4 times d square. Okay, so not yet. Is it? So we don't have d yet. We've not defined d, which is the beam diameter. We're going to continue. Pulse width, which is 0.5 milliseconds. It's a long pulse. Which is 0.6 millimeters. So a huge beam. See now, D is defined, so there's a number there in the energy density. Let's save this as single laser pulse live demo. We have emissivity, which is a material property. It's dimensionless. I'm going to write ME here. Is heat transfer coefficient? I want to write. I'm going to call it H1 so that I don't know what H is in COMSOL, so it might, so that it just doesn't clash with any underlying code. Just put a number next to it. Absorptivity, even A, you could just say A1 just to be sure, which is 0.25. There's half width of the curve, which is, we want to call it dt, bigger dt, which is 30 Kelvin. Reference, it's called XR. 100,000 micron. This is the reference point of the laser beam where it is on the surface, basically. Then we have a standard deviation of the laser beam, since it is a, I'm going to say XD. It is a Gaussian laser beam, so you would want that Gaussian distribution there. Ambient temperature is TA 293.15 Kelvin. Hi. The initial temperature, TI, just same as this value here. Stefan Boltzmann constant. I'm going to say Steph constant. It is, what's the value? 5,67 E negative 8 watt per meter square per. Very interesting. 6.4 closing brackets. Then we have the universal gas constant, which is R, I'm going to write RG constant so that it doesn't. 8,314 joules per mole per Kelvin. And we have the gravitational acceleration with a GR const, which is 9,81 meters per second square. Okay, so these are the properties. Do we need to add something else? No. Okay, so these are the properties of that we're going to use for the simulation. I think we need to add something else as well, which is the dimensions of the sample. Ideally, you would want to add them at parameters so that it is much easier to edit the sample. There it is. So in this sample here, or geometry, we have two rectangles. We have the outer rectangle, bigger rectangle, and then we have an inner rectangle there, which is 600 micron and 2000 micron in height. So I'm going to say H1, which is for the rectangle, the first, the bigger one, which is 2500 micron. I'm going to say height of the outer rectangle. The question that you might have is height of the smaller rectangle. You might ask yourself, why two rectangles? It is a very smart way of focusing the mesh. You know that the laser beam will be landing on this surface here, not everywhere. So you would want to find a mesh here. And then you'll have a coarse mesh outside. you're trying to be very economical and make sure that you save computational time. So this is the inner rectangle. Then we have, I'm going to say just width, W1, could be length, doesn't matter. This is 2000 micron width. I'm lazy. Let's make this bigger. I'm going to change this to width of the inner rectangle. And then we have W2. Oh, this is not inner, it's outer. Well, let's copy it and put it here. This is the outer. It is 600 micron, the inner. Saving it. Now, I think we've created that and that. So we've inserted these conditions or these parameters. Now, we are going to move into the component. The component here, we have to first define a few things. We have to define what is the laser, the equations for the laser beam. And we have to define the, I'm going to expand this so that we see what I'm referring to here. In this model, the author defines the average laser power density in the Gaussian distribution. There's the equation right here, this equation. The equation has three terms. First, that's the absorptivity of the sample. Then we have the average energy density, and then you have the Gaussian distribution. So we are not going to write the equation, this is straight like this, and we're going to split it into exactly these components. So first we're going to have this, let's create this for just this equation here, which is the energy density. I'm going to zoom in. So this is where we are. So you would want to have this under, you right click under definitions and variables. Okay. Let's say energy density, let me call that ED. It is EP divided by pulse width multiplied by pi over 4. Let me open a bracket here and multiply by d squared. Close the bracket. So this is the energy density. That's the average energy density. And then it also has Gaussian space, this one. It defines the distribution of the laser beam, where the x, which is the space, minus xr, which is the position. square that divided by 2 times the standard deviation square. So I'm going to say here G space, which is the Gaussian space or Gaussian distribution. Alright, so it is exp open bracket minus open bracket, and as a third bracket x minus xr square divided by 2 times xd, since we called that xd, close the bracket, and it's now in trouble. There's a lot of brackets here. Okay, so there's our Gaussian space. Now we can now say, right, what is the laser heat source? So we're going to say PG, it is I said this is A1, absorptivity, multiplied by the energy density, multiplied by the Gaussian space. So there is our laser heat source. This laser heat source is not doing anything. It is fixed because there is no term here that is giving it motion on the Gaussian distribution. You would change it here on the XR. XR would be a transient term if we were talking about a moving laser beam. But today it's a fixed heat source with 1 pulse, so it should be the easiest thing to do if we're choosing not to complicate our lives. Okay, so you're going to add another feature of the laser. The laser beam is pulsing. If you look closely, you read this article, the author described the laser as a pulsing laser heat source. So which means that I'm going to scroll there. So we're going to now try and incorporate this right here, where the laser is on for a certain time, which is the time T1, and it says T1 is the pulse width. And then after that, it is off until time T2, which is now this space here is 1 over f, which is 1 over the pulse repetition rate. And the next pulse comes in after T2 for it is on for a time that is equivalent to the pulse width, and it repeats. So what now, how we included this into the equations is he used, I'm zooming in here so that it is much easier there. So in this equation you have pulse, which is this is an energy balance equation. Pulse, that's a laser pulse, and this B term here, this B term is an on and off parameter, which he used this function to represent it with. So we're going to create this function and explained that it was an analytic function. So there are two functions here. You have a rectangular function, and then you have this entire term now, which allows for the modulation of the laser beam. So let's see if we can do that. We're going to come here and functions. There's the rectangular pulse. This is the rect one he's talking about there. Now this, under parameters here, the upper limit of this rectangular waveform is pulse width, because it is on for a time that is equivalent to the pulse width. I'm going to zoom in now. If we plot this, transition zone is too large. Two transition zones overlap. So we need to smoothen this. Do I really need to smoothen it? No. Okay. So there's our rectangular pulse. It's not a distribution of the pulse, but it's just an on and off equation that we're going to use to say that the pulse is on for pulse width, time equivalent to the pulse width. Now we're going to create an analytic function that we're going to call B for some reason. Let's call it pulse. Do we have to call it pulse so that we see it? This we call B. What is the expression? Well, the expression is rect1 mod T 1 over F close bracket argument. Argument is T. This is in seconds. No units there for now. And then let's see if on the plot parameters 1 over F. So you want to see the pulse. There it is. Let me make it smaller. Let's say 0.1 times 1 over F. I want to see it. There it is. We see that here it is yellow, meaning that it's an inconsistent unit. How can we fix this? If we make this 1 over S, it's not helping. Okay, let's make this second. 1 over S. Okay, there it is. Okay, so the pulse is on for 1 over F, meaning that, let's say, let's look at this article here. This article has, let's look at the plots themselves. When does the pulse end? It ends at 1 point, let's say at 1 second. Do we want that? Okay, let's see what it looks like. Let's end it at 1 second. Okay. Lots of pulses coming in. Let's end it at 1 over F. We want 1 pulse, and I'm going to make it just 80% of the pulse of this duration, not all of it. Okay, so now we have this equation. Now we have to go and call it right there under variables. We're going to come and bring it here and say multiply by B. Okay. Right, so there's our laser pulse. And then I think we're done with this part. We're going to move on. First we save. So now let's go to geometries. We have two rectangles. We have the first rectangle with a width. This is going to be very interesting. Width 2, the bigger one, and height 2. Build it. And then we create another rectangle, outer rectangle, with a width 1 and height 1. Okay. What is happening here is that we want to move this right here. What do we want it? It must be at the center of this. Right. So let's say the rectangle 1 is half the width. If we say around x, we're moving it now. Good God. So it's finished. It goes past it, and then we say half of that width. Okay. Minus, let me say h2. Like that. Oh, problem solving. Dear God. Okay, so the position of the laser beam, the rectangles, rectangle 1, the smallest one, is half of a difference between the rectangles. And then moving it up, say a difference between the two rectangles in terms of the heights as well. Right, so we have this geometry. Now we're moving on to creating the material. We have the material already, so we say add material that we created in our previous demonstration. There it is. Double click on it. Okay, already it's selecting the parameters that it wants, the heat transfer physics, which is good. We're moving on, we're saving. Now we're here. Here, what we want is to insert the most fundamental. We're not going to complicate it and introduce phase change yet. We're just going to include a heat flux and heat loss by radiation and another term for cooling. So here you have first heat flux. I'm going to call this heat flux laser. Just laser. And this laser is inward heat flux PG. We called it PG. And it lands on that spot right there. Selecting by clicking that boundary there. And then we add another heat flux. This is, I'm going to call it convection, which is cooling, and it is applicable here, there, and convective heat flux as H1, external temperature T0. Did we call it TA, ambient temperature? Remember we called it TA here. If we expand this node, TA there, and we call that heat transfer coefficient H1. So there you see it. Okay. There is cooling also on the sides. I'm following the guideline here in this article because as you could see here, that is convective cooling 3 and 8 and 1 and 9. And so going back to the geometry there, there's 3, 8, 1, and 9. 9, 8, 3, and 8. That's where he applied the convective cooling and radiation losses. So let us add the radiation losses down here. Diffuse surface applied on these boundaries as well. Emissivity, I call that user defined ME. We called it ME here. Remember, if you scroll down here, there it is. We called it ME. Okay. So I think we are done with the laser, the heat transfer features. We're going to mesh now. If we say it's a physics controlled mesh, let's build it. It's a very coarse mesh, but based on their description here, it's saying that the mesh maximum size of the elements is 14 micron. The minimum is 2 micron. Okay. So we have to say we add a free triangular mesh, and I'm going to add 2 of them. The first one, that size here, this one is applicable only in this region domain here, not in the entire geometry, just here. And the second one is in the remaining. So since the specified element sizes, let's include them here. So the maximum element size is 14 micron and minimum is 2 micron. Maximum is 14 micron. I could write UM, see what happens. This is 2 micron. Build all. There it is. Very interesting. Right. So we save. I think we're done with meshing. And then the study. I think that's fine. Oh, is it? Let's change this to 1/f. And let's make this smaller, 0.001. I could have it as pulse width divided by some value. Could do that. Let's do that. Let's say divide the pulse width divided by 100. Okay, we save. I would like to show default solvers so that I can modify here the time stepping to make it intermediate. Okay, let us see what happens if we compute. Looking at the progress, if it goes over 5%, we're fine. There's a convergence plot. The computation has completed. However, what we did not do is to add a probe so that we can actually plot the surface temperature up there at the center of the laser spot. So let us add a probe here, a domain probe. This domain probe will only be applicable only to this smaller rectangle. Then the computation took very long, so let us make this time step very small, to divide it by 10, not by 100, and make this 20% of the period. Okay, and let's delete the solvers again, and change the step, take it by solver to intermediate, and compute again. Should be faster than the other simulation that we just did. This is the final simulation. You can see the laser spot there, and if we look at the probe plot, we could see that the heating cycle temperature rises until it reaches about 10,000, and we have the cooling cycle and your phase change kinetics occurring, and it cools until it reaches some temperature around room temperature there. So an assumption there is would be even after the end of the period, it would be at temperatures very low, which are at room temperature basically. So basically that was this is the end of the demonstration, and you can see that one pulse landed here, and we're successfully able to simulate this.